Hello, and welcome to Boring History for Sleep. Tonight, we will be examining an object of such profound ubiquity that it has become essentially invisible. It is a silent, unmoving sentinel, a piece of civic furniture that governs the rhythm of our daily lives from above. Suspended over countless intersections is the humble traffic signal, but our focus is not on the signal itself. The red, yellow, and green lights are a story for another time. Instead, our attention will be drawn to its support system, the mounting bracket and the mast arm. It is the simple, yet surprisingly complex piece of hardware that connects the signal head to its pole. It is a testament to a quiet, decades-long conversation among engineers, a slow, deliberate evolution driven by the unglamorous metrics of safety, durability, and cost efficiency. To truly understand the peaceful, ordered flow of our modern streets, we must first appreciate the subtle engineering and painstaking standardization of the devices that hold it all together. To begin our journey into this specific corner of urban infrastructure, we must first establish the landscape of the pre-war era, before 1940. In these early days of traffic control, the concept of standardization was largely a theoretical ideal, rarely implemented in practice. Cities and towns across America, grappling with the burgeoning chaos of the automobile, devised their own solutions with little intermunicipal coordination. The most common method for displaying a traffic signal was the simple post mount. A signal head, often a heavy cast-iron affair with a single, central, four-way face, would be bolted directly to the top of a pedestal or a simple metal pole positioned at the corner of an intersection. Sometimes, individual one-way signal heads were clamped directly to the side of a utility pole using simple band clamps, not dissimilar to those used for securing signs. The brackets of this era, if they could even be called that, were rudimentary. Often, a signal head would have an integral mounting boss cast directly into its housing. This boss would feature a threaded opening, typically for a standard pipe thread, allowing it to be screwed onto a vertical pipe riser. For side-of-pole mounting, a simple L-shaped piece of cast iron or forged steel might be used, with one end bolted to the pole and the other end providing a threaded stud for the signal. These were not products of sophisticated engineering analysis, but rather of practical, foundry-based solutions. The primary concerns were simply holding the weight of the signal and resisting the elements. Wind load calculations were nascent, and the dynamic forces of vibration were poorly understood. Another popular method of the time was the span wire installation. Two poles would be erected on opposite corners of an intersection, and a steel cable or span wire would be stretched between them. The traffic signal would then be suspended from the center of this wire, hanging down over the intersection. The bracket, in this case, was a simple wire clamp and a hanger assembly. While this method provided excellent visibility by placing the signal directly in the driver's line of sight, it had significant drawbacks. The signal was susceptible to swaying in the wind, which could be distracting and even dangerous. The constant motion placed stress on the electrical cable feeding the signal, leading to premature failure. Furthermore, maintenance was difficult, often requiring a lineman to access the signal from a ladder placed in the middle of an active intersection. The attachment methods were simple. U-bolts, cable clamps, and turnbuckles were the primary tools for tensioning the wire and securing the signal. There was no uniformity in the size of the U-bolts, the gauge of the wire, or the design of the hanger. Each city, and sometimes each intersection, was a unique ecosystem of parts. This lack of standardization presented a significant logistical challenge for municipal public works departments. A city might have traffic signals sourced from multiple manufacturers, Krauss-Heinz, Marbolite, Eagle signal, and each might use a different mounting thread size or bolt pattern. This meant that a storeroom had to be filled with a wide variety of incompatible parts. A bracket for an Eagle signal might not fit a Krauss-Heinz signal. A damaged pole mount could not be easily replaced with a part from a different supplier. Maintenance crews had to be trained on a multitude of different systems, and their trucks had to be stocked with a dizzying array of fasteners, brackets, and fittings. This inefficiency was a quiet but constant drain on municipal budgets and manpower. The need for a more rational, systematic approach was becoming increasingly apparent. Though the catalyst for significant change had not yet arrived, the materials of this era were robust but crude by later standards. Cast iron was prevalent for its low cost and the ease with which it could be formed into complex shapes. Steel was used for poles and span wires, often with a simple coat of paint for corrosion protection, a solution that required constant upkeep. The science of galvanization was known, but not yet universally applied to this type of civic hardware. The result was a landscape of signals that were heavy, prone to rust, and difficult to service. The brackets were often overbuilt in terms of sheer mass to compensate for the uncertainties of the material and the unknown forces they would face. It was a system born of necessity, but it was not yet a system born of engineering. The 1940s, dominated by the Second World War, saw a period of relative stagnation in the development of civilian infrastructure. Material and manufacturing capacity were diverted to the war effort. Steel, copper, and other essential materials were strictly rationed, and municipal projects were often postponed. However, the immense industrial mobilization of the war had a profound, if delayed, effect on the post-war world of traffic signal mounting. The war effort spurred incredible advancements in metallurgy, manufacturing processes, and most importantly, the discipline of systems engineering. Techniques for mass production and standardization, honed to produce aircraft, tanks, and ships with interchangeable parts, would soon be applied to the more mundane world of urban hardware. When the war ended, America experienced an unprecedented economic boom and a surge in automobile ownership. Suburbs expanded rapidly, and with them came a vast network of new roads and consequently new intersections requiring signalization. The old methods of post-mounting and simple span wires were no longer adequate for the wider, multi-lane arterial roads that were becoming common. A signal mounted on a corner post was often invisible to a driver in the inner lanes. The center span wire signal, while visible, was still mechanically problematic. A new solution was needed, one that could position the signal heads out over the roadway, directly in front of the approaching lanes of traffic. This need gave rise to the widespread adoption of the mast arm. While rudimentary forms existed before the war, the post-war era saw its development and proliferation. The earliest mast arms of the late 1940s and early 1950s were simple, utilitarian structures. They were typically constructed from standard galvanized steel pipe, often in 2-inch or 3-inch diameters. A simple L or J shape was created by welding a horizontal pipe to a vertical riser, which was then clamped to the main traffic pole. The brackets for attaching the signal heads to this new type of arm were, in turn, quite simple. A common design was the pipe clamp or saddle bracket. This consisted of a 2-piece casting, usually of aluminum or galvanized malleable iron. One piece was a saddle that conformed to the curvature of the mast arm pipe. The other was a cap. The 2 pieces would be placed around the arm and bolted together, clamping the bracket firmly in place. Protruding from this clamp assembly would be a threaded hub, typically with a 1.5-inch national pipe thread, onto which the signal head could be screwed. This design was a significant step forward. It allowed for adjustability. A maintenance worker could loosen the bolts and slide the entire signal assembly along the mast arm to position it precisely over the lane. It also allowed for rotation to aim the signal face correctly. However, these early designs were not without their flaws. The clamping force had to be just right. If too loose, the signal could rotate or slip under its own weight or in high winds. If too tight, the bolts could deform the hollow mast arm pipe, creating a weak point. The constant vibration from wind and passing traffic could also cause the clamping bolts to slowly loosen over time, requiring periodic retightening. The attachment of the mast arm itself to the vertical pole was another area of early innovation. The simplest method involved U-bolts. A pair of heavy-duty U-bolts would wrap around the main pole, with their threaded ends passing through a flange plate welded to the vertical part of the mast arm assembly. This was a strong and simple connection, but it concentrated stress on the pole and could be difficult to install perfectly plumb and level. Another emerging design was the 4-bolt attachment. Here, the mast arm terminated in a flat flange plate with 4 holes. This plate would be bolted directly to the side of the pole, which had been pre-drilled with a matching 4-hole pattern. This provided a more rigid and stable connection, but it lacked the adjustability of the U-bolt clamp. The location was fixed. This dichotomy between adjustability and rigidity would be a recurring theme in the evolution of mounting hardware. During the 1950s, as the interstate highway system began to take shape following the Federal Aid Highway Act of 1956, the scale of road engineering grew dramatically. Intersections became larger and more complex. This demanded longer mast arms and more robust signal supports. The simple bent pipe mast arms began to reach their structural limits. A long piece of 2-inch pipe, burdened with several heavy signal heads, would sag noticeably. In the wind, it would oscillate, creating metal fatigue at the connection points. Engineers began to experiment with truss designs to increase strength without adding excessive weight. A simple truss mast arm might consist of 2 parallel pipes, an upper and a lower chord, connected by a web of smaller diagonal or vertical pipe sections. This design was significantly more rigid than a single pipe and could support heavier loads over longer spans. The brackets for these new truss arms had to adapt. A simple saddle clamp designed for a single pipe would not work. Instead, custom mounting plates were developed. A signal head might be attached to a short vertical pipe, which was then clamped or bolted between the 2 chords of the truss. This added complexity to the installation, but provided a much more stable platform for the signal. The materials were also slowly improving. Hot dip galvanizing became the standard for protecting steel components from corrosion. This process involves dipping the fabricated steel part in a bath of molten zinc, which forms a durable, metallurgically bonded coating. Aluminum, with its inherent corrosion resistance and light weight, began to see more use, particularly for the signal head housings and the mounting brackets themselves. Cast aluminum brackets were common, as the casting process allowed for more complex shapes that could better distribute stress. However, a lack of national standards was still a persistent issue. A city engineer in Ohio might specify a truss arm from one manufacturer, while a counterpart in California might use a tapered monotube arm from another. The bolt patterns for the arm-to-pole connection were not consistent. The spacing of the chords on a truss arm from Company A might be different from that of Company B, requiring different mounting brackets. This meant that components were still not interchangeable. This lack of interoperability was a source of frustration for traffic engineers and public works directors who were trying to manage increasingly complex signal systems on tight budgets. The first steps toward addressing this came not from a single national mandate, but from the collaborative efforts of professional organizations. The Institute of Transportation Engineers, or ITE, became a crucial forum for these discussions. Through its committees and publications, the ITE began to develop recommended practices. These were not legally binding regulations, but they represented a consensus among professionals about best practices. They began to publish guidelines on signal visibility, placement, and the structural requirements for supports. These early ITE publications began to suggest, for instance, standard heights for mounting signals and minimum clearances over the roadway. This was the beginning of a slow, incremental convergence towards standardization. A city writing a specification for a new traffic signal installation could now reference an ITE recommended practice, giving it more technical weight and ensuring a certain level of quality and consistency. The 1960s marked a period of significant refinement in the design of traffic signal supports. The lessons learned from the rapid expansion of the 1950s were being analyzed, and engineering was becoming more sophisticated. The simple pipe and truss mast arms were now being joined by a new design, the tapered monotube arm. These arms were fabricated from a single sheet of steel, which was cut into a trapezoidal shape and then cold-formed into a round or multi-sided tube that was wider at the base and tapered towards the end. The seam was then electrically welded. This design was both aesthetically cleaner and structurally more efficient than the open truss design. It offered better aerodynamic performance, reducing wind-induced vibrations, and it had fewer surfaces to collect dirt, water, and corrosive agents. The attachment of the signal heads to these new tapered arms required a new generation of brackets, the simple two-piece saddle clamp was no longer ideal, as the diameter of the arm was constantly changing. A clamp designed for the arm 10 feet from the pole would not fit the arm 20 feet from the pole. To solve this, manufacturers developed adjustable banding brackets. These brackets used stainless steel bands, similar to large hose clamps, that could be wrapped around the arm and tensioned with a screw mechanism. The bracket body itself would be held against the arm by the tension of the bands. This allowed a single bracket design to be used at any point along the tapered arm. Another solution was the use of pre-drilled and tapped holes in the mast arm itself. The manufacturer would weld a reinforcing plate and a threaded boss on the inside of the arm before galvanizing, and the signal bracket could then be bolted directly to the arm at these specified locations. This provided a very clean and secure attachment, but it sacrificed the on-site adjustability of the banding bracket. The choice between these two methods often came down to a trade-off between installation flexibility and long-term stability. The connection of the mast arm to the vertical pole also saw significant evolution during this decade. The simple flange plate with 4 bolts became the de facto standard for new installations. However, the details of this connection were refined. To distribute the immense stress at this critical joint, reinforcing plates, or collars, were often welded to the main pole around the attachment point. The flange plates themselves grew thicker, and the use of high-strength, galvanized, grade 5 or grade 8 bolts became common. Engineers began performing more rigorous stress analysis, considering not only the static weight of the arm and signals, but also the dynamic loads from wind gusts and the cyclical loading that could lead to metal fatigue. One of the most significant and subtle areas of standardization that emerged in the 1960s was the signal head mounting itself. For decades, signal heads were attached via a 1.5-inch pipe thread. The signal housing had a threaded boss on the top and bottom. A bracket would have a corresponding threaded stud, and the signal was simply screwed on and secured with a lock nut. This was simple, but it had a major flaw. To aim the signal, a worker had to loosen the lock nut and physically rotate the entire heavy signal head. Fine-tuning the alignment was difficult. The introduction of the serrated, adjustable knuckle changed everything. This new mounting system consisted of 2 matching discs, each with a pattern of interlocking radial serrations or teeth on one face. One disc was attached to the signal head, and the other to the mounting bracket. A central bolt passed through both discs, clamping them together. When the bolt was loosened slightly, the 2 serrated faces could be disengaged, allowing the signal head to be rotated in precise incremental steps. Each click of the teeth represented a small, fixed angle of rotation, often 5 degrees. Once the desired angle was achieved, the central bolt was tightened, locking the teeth together in a positive, vibration-proof connection. This same serrated knuckle design was often used at the point where the bracket attached to the mast arm clamp, allowing for vertical tilting of the signal. This tri-knuckle, or 3-way adjustable bracket, allowing for horizontal rotation at the signal, vertical tilting, and positional adjustment along the arm, became an industry standard. It dramatically simplified the process of aiming signals, making it faster, more precise, and safer for maintenance personnel. This seemingly small innovation had a profound impact on the efficiency and quality of traffic signal installations nationwide. It was a perfect example of standardization driven by practical, field-level needs. Another area of quiet standardization was in the electrical connection. In early installations, the wires for the signal lamps would pass through the hollow bracket and into the signal head, where they would be connected to terminals with individual screws. This was a time-consuming and error-prone process. During the 1960s, NEMA, the National Electrical Manufacturers Association, began to develop standards for electrical connectors. This led to the adoption of standardized circular multi-pin connectors for traffic signals. A plug from the mast arm wiring could be quickly and securely connected to a receptacle on the signal head. This made replacing a damaged signal head a much faster plug-and-play operation, reducing traffic disruption and the time a worker had to spend in a vulnerable position. The mounting bracket began to be seen not just as a structural element, but as part of an integrated electromechanical system. Designs started to incorporate weatherproof access plates and larger internal passages to make pulling wires easier. The 1970s can be characterized as the era of systems engineering and materials science in traffic control hardware. The groundwork of standardization laid in the 1960s was now being built upon, and the focus shifted to optimization, durability, and safety. The monotube mast arm, in both round and octagonal cross-sections, had become the dominant design for new installations. The choice of shape was often a matter of manufacturing preference and aesthetic considerations, though engineers debated the relative merits of each in terms of wind resistance and strength-to-weight ratios. A major focus of this period was understanding and mitigating the effects of wind-induced vibration. Long mast arms, especially those in open, windy areas, were susceptible to a phenomenon known as aeroelastic flutter or galloping. This is a high-amplitude, low-frequency oscillation caused by the way wind flows over the structure. This constant, sometimes violent motion could cause premature fatigue failure at the welds and connection points. To combat this, engineers began incorporating vibration dampeners into their designs. A common type of dampener was a simple Stockbridge damper. Similar to those seen on high-voltage power lines, it consisted of a short length of steel cable with weights at each end, clamped to the tip of the mast arm. The damper was tuned to oscillate out of phase with the natural frequency of the arm, effectively cancelling out the harmful vibrations. Other designs integrated dampening mechanisms directly into the signal mounting brackets. These might include elastomeric pads or spring-loaded assemblies that would absorb some of the vibrational energy before it could be transmitted to the signal head itself. The materials used for brackets and arms also continued to evolve. While galvanized steel remained the most common material for poles and arms due to its strength and cost, aluminum alloys became increasingly popular for brackets and signal housings. The 60R61 T6 aluminum alloy, a precipitation-hardened alloy containing magnesium and silicon, offered an excellent combination of strength, lightweight, and corrosion resistance. New manufacturing techniques, such as improved die casting, allowed for the production of highly detailed and dimensionally accurate aluminum brackets with minimal secondary machining. This reduced costs and improved consistency. The attachment of the mast arm to the pole underwent further refinement. While the bolted flange plate was standard, a new design emerged for attaching arms to poles, known as the slip-fitter connection, particularly for smaller arms or luminaire arms on the same pole. This involved a vertical tenon on the top of the pole. The mast arm would have a larger diameter base that would slip over this tenon and be secured by a series of set screws. This was a self-leveling and simple connection method, though less common for very large, heavy traffic signal arms. For the primary traffic signal arms, the focus was on improving the bolted flange connection. Specifications became more rigorous, detailing not just the number and size of bolts, but also the required material grade, the method of tightening, turn of the nut or calibrated wrench, and the specific torque values. The goal was to create a connection that was rigid enough to resist wind loads, but had enough carefully engineered flexibility to handle thermal expansion and contraction without overstressing the fasteners. Safety became a more prominent concern in the design of the entire support structure. The concept of breakaway supports began to gain traction, particularly for poles located in vulnerable roadside locations. A breakaway base is designed to shear or fracture in a controlled manner when struck by a vehicle, allowing the pole to move out of the path of the vehicle and reducing the severity of the collision. The earliest breakaway designs included cast aluminum transformer bases with frangible corners or slip bases that were clamped together with high-tension bolts designed to slip under impact. While this applied more to the base of the pole than the mast arm bracket itself, it was part of a holistic view of the traffic signal support as a complete system that had to perform safely under all conditions, including failure. Inside the brackets and arms, more attention was paid to the wireway, the path for the electrical cables. Early designs often had sharp edges or weld slag inside the pipes that could chafe and damage wire insulation over time, leading to electrical shorts. New standards began to call for deburred and smooth interior surfaces. Grommets made of nylon or neoprene were specified for any point where wires passed through a hole in a metal wall, protecting them from abrasion. The internal volume of the arms and brackets was also considered, ensuring enough space for the required number of wires without excessive bending or crowding. Terminal blocks, small strips of insulating material with screw terminals for joining wires, were often mounted inside a weatherproof enclosure at the end of the mast arm or within a specialized terminal bracket. This created a neat, organized, and easily accessible point for connecting the individual signal head cables to the main trunk cable running from the controller cabinet. This level of detailed, systematic thinking replaced the old ad hoc approach. The standardization efforts of the ITE and AASHTO, the American Association of State Highway and Transportation Officials, continued to gain influence. State departments of transportation began to develop their own standard drawings, or standard specifications, for traffic signal installations. These were highly detailed documents, often running to hundreds of pages, that specified every single component of a signal installation, from the concrete foundation to the type of lock washer used on the bracket bolts. An engineer designing an intersection in that state would simply reference a particular standard drawing. For example, Standard Drawing TS4B, 30-foot mast arm assembly with luminaire extension. This drawing would specify the exact dimensions of the arm, the thickness of the steel, the weld details, the bolt pattern for the pole connection, and the part numbers for the approved signal mounting brackets. This had a profound effect on the manufacturing industry. A manufacturer wishing to sell traffic signal hardware in a particular state had to ensure their products met that state's standard specifications. This forced a convergence of design. While there were still regional variations, a 5-bolt signal mounting bracket made by a company in Illinois would now have the same serrations, the same bolt circle diameter, and the same NEMA connector cutout as one made by a company in Pennsylvania, provided both were designed to meet a common AASHTO or state DOT standard. This interchangeability was the goal that had been sought for decades. It meant a state or city could source parts from multiple approved vendors, fostering competition and lowering prices. It meant a maintenance crew could be confident that a replacement bracket from their stock would fit the signal in the field, regardless of the original manufacturer. This quiet, bureaucratic process of specification and standardization was perhaps the single most important development in the history of the traffic signal bracket. The 1980s saw the widespread adoption of computers in the engineering and design process, which brought a new level of optimization to traffic signal structures. Computer-aided design, CAD, software allowed engineers to create detailed 3D models of mast arms and brackets. More importantly, finite element analysis, FEA, software allowed them to simulate how these structures would behave under various loads. An engineer could apply a simulated wind load from a hurricane, and the software would display a color-coded map of the stress concentrations in the model. This allowed designers to identify potential weak points and add reinforcement precisely where it was needed, without adding unnecessary weight and cost. They could optimize the shape of a flange plate or the thickness of a casting to achieve the maximum strength with the minimum amount of material. This computational power led to more refined mast arm designs. While round and octagonal tubes were still common, more complex shapes, such as 12-sided or 16-sided dodecagonal or hexadecagonal cross-sections, became more feasible to manufacture and analyze. These multi-sided tubes provided a good compromise between the aerodynamic properties of a round tube and the ease of fabrication of a square tube. The welding processes also improved, with automated seam welding creating more consistent and reliable joints. In the realm of mounting brackets, this era saw the refinement of existing designs rather than radical new inventions. The serrated, adjustable knuckle was a mature and universally accepted technology. The focus was on improving its durability. The serrations were designed with specific tooth profiles to maximize locking force and resist wear. The materials were improved, with some designs using stainless steel inserts for the serrated faces to prevent corrosion from locking them together over time. The hardware, the central bolt, nuts, and washers, was increasingly specified as stainless steel for its longevity and resistance to seizing, especially in coastal areas or regions that used road salt in the winter. Another area of focus was corrosion protection. While hot-dip galvanizing was an excellent protective coating, it could be damaged during shipping and installation, and its dull grey appearance was not always aesthetically pleasing. The 1980s saw the rise of advanced coating systems, such as powder coating. In this process, a dry, powdered polymer is electrostatically applied to the metal part, which is then heated in an oven. The powder melts and flows into a smooth, hard, and durable finish. This offered a wider range of colors and a more uniform appearance than paint, and it was more durable than many paint systems. Often, a duplex system would be used, where a bracket or pole would be hot-dip galvanized first and then powder-coated on top, providing 2 layers of protection against the elements. The increasing complexity of signal displays also drove bracket design. The standard 3-section, red, yellow, green, signal was now frequently supplemented with protected turn arrows. This led to 4-section and 5-section signal heads, often arranged in a cluster or a doghouse configuration, with the green arrow sections at the bottom. These larger, heavier, and more oddly shaped assemblies required stronger and more versatile mounting systems. Bracket designs evolved to include longer arms and multiple attachment points to securely hold these complex signal arrays. The need to mount signals for multiple lanes from a single mast arm led to the development of cluster or gantry-style mounts, which were essentially smaller subframes that clamped to the mast arm and provided standardized mounting points for several signal heads. The attachment of the mast arm to the pole had by this point become highly standardized around the flanged connection. However, the design of the pole itself had evolved. Instead of being a single continuous tube, poles were often designed with a handhole near the base. This was a small, covered opening that provided access to the wiring and terminal blocks inside the pole. The cover for this handhole had to be designed to be secure and weatherproof, yet easily removable for maintenance. The pole base plate, which is welded to the bottom of the pole and used to anchor it to the concrete foundation, also became a subject of intense standardization. AASHTO published standards for the design of these base plates and the associated anchor bolts, specifying the bolt circle diameter, the number of bolts, and the material strength for poles of a given height and load capacity. This ensured that a pole from one manufacturer could be installed on a foundation prepared for a pole from another, a critical element of interoperability. By the end of our period of study, in 1990, the world of the traffic signal mounting bracket and mast arm was one of mature, incremental standardization. The chaotic, ad hoc landscape of the pre-war era had been replaced by a highly regulated and deeply specified system. The journey from a simple cast iron clamp to a computer-designed, powder-coated aluminum alloy bracket was complete. The simple L-shaped pipe arm had evolved into a tapered, dodecagonal, FEA-optimized structure. What had been achieved over these 50 years was the creation of an invisible but essential language of engineering, a language spoken in bolt patterns, thread sizes, NEMA connector standards, and AASHTO material specifications. This common language allowed a complex system of parts from dozens of manufacturers in different states to fit together seamlessly at an intersection in a small town. It allowed public works departments to maintain their vital infrastructure efficiently and cost-effectively. It ensured that the signal head, the critical element of communication between the traffic engineer and the driver, was held securely and reliably in the correct position, day after day, year after year. The next time you find yourself waiting at a red light, you might take a moment to look up. Look past the light itself and notice the hardware that holds it. See the gentle taper of the mast arm, the clean lines of the flange connection at the pole, and the compact, functional form of the mounting bracket. It is not an object of great beauty or excitement. It is an object of quiet competence. It is the physical manifestation of 50 years of slow, careful thought, of countless committee meetings, of thousands of pages of specifications, and of the dedication of engineers to solving a simple problem: how to hold a light in the air safely and reliably. It is a monument to the unglamorous but essential process of standardization, a silent framework that underpins the rhythm and safety of our modern world.